Flack math! Give me some math and I'll give you some flack. Flack math!
Okay, so we're doing 47. We are going to graph
Just like focus out.
exponential equations. Exponential equations are confusing, but graphing them is just plugging and chugging, and we'll get there. Okay. So function of the form y equals a b to the x. Okay. So a is like your coefficient, b is your variable, and x is your exponent. But usually they'll give you this, and so your x, y. If you were going to plot points, you would pick your x's and y's here. Okay. So this is an exponential function. Okay. So here's what the parent function looks like, or the mother function, remember? So the parent function looks like this. So this is like y equals nothing times b to the x. And this is where b is greater than 1. So it's not a fraction. It's just where b is greater than 1. Okay, this is a representation of y equals b to the x, where b is in between 0 and 1. So this is still y equals b to the x, but b is in between 0 and 1. Okay, so it's a fraction. All right, so this is what a fractional exponential function looks like. We're not, and that's kind of a weird, it's because it's not a fractional exponent. Just the b is the fraction, okay? So it's amazing how much that changes it. All right, now here's a fun word, and this is called an asymptote. Asymptote is a line that something approaches but never really touches. So for example, this would be called the asymptote. I think that's how you spell it. Yep.
Oh yeah.
Okay, so for the graph above, y equals 0. These are both asymptotes.
So they never touch the x-axis.
Right, they get really close, but they never touch it. Okay, so here's a good definition: is a line that a graph approaches as the value of the variable becomes extremely large or small. Okay, so it's basically a line that a graph approaches but never touches.
No matter how big of number we put in, it'll never touch it.
Right.
So it's parallel, but not quite.
Yeah. So it's never quite reaching parallelity. I'm gonna say that's a word.
But if we went to a really, really big, if it's never quite parallel, then they would intersect.
Yeah, they would intersect if it never becomes parallel.
No, that's the weird one, because there's always a little bit of an angle. It never quite straightens out.
What?
If it
Wait,
straightens
that makes
out.
no sense because at some point it's going to reach that line.
So
No.
It would have to reach the line.
See, that's the weird thing, because remember this demonstration where you can always get infinitely closer. You can always cut that distance in half. Theoretically, physically, you can't. You're just not that cool. Okay, but
Are you that cool?
the same thing here. Just think about it. It will always get closer and closer and closer, but never touch it. So it never reaches parallelity.
It continues to go downward.
It's like
Yes.
Infinitely.
Yes.
It has to intersect this line. If it's infinitely going down, either it has to become parallel or starts going up.
Yeah.
But
So
that
like
means
the
there
next
has to be a
value,
parallel.
the next value gets closer. The next value gets closer. The next value gets
Yeah,
closer.
so if it is gonna get
Is
close
this
enough
like
to
a
touch
Bible
it.
theory or something? I don't know.
Bible?
I'm just wondering.
It's
Because you can't
fractionally
explain it.
closer.
I think I do understand it. Because there's always a tiny bit of curve in the line too. The line's not
Yes.
directly straight.
Yes.
It's always curved a tiny bit.
Both of them are going on infinitely, aren't they?
So,
So
yeah,
then it's not like you can like be going through the point but then like miss it, like because it like stopped.
Right. right.
Mm.
So it's like this force field, like that's protecting it from touching that line. So think of an asymptote like that. So
I
it's
know
always
what
approaching that, but it's never touching it. It's crazy.
Way too
You
confusing.
can divide a number in half.
Yeah, you can divide a number in half infinite number of times, and it'll never be zero.
Until it is.
No.
We should test
It
this
is.
theory.
Okay, so here's what we're gonna do. We're going to graph.
Oh, I see what you're saying.
We're going to graph this function. Graph y equals 2 to the x. Okay? So this is how you graph this function. You don't have to worry about intercepts and slope or anything like that. You just have to create a chart. So let's create a chart. They always, for some reason, they switched from these vertical things to horizontal things. It's just whatever. So let's pick an x. What's the easiest x to pick?
0.
0. When x is 0,
But x is never 0. No, it is. No, it is right there. Right.
when x is
Y
0,
is never
It
0.
cancels out.
makes this a 1, right?
Yeah.
2 to the 0 is 1, so y equals 1. What about when x is 1? What's y? 2. What about when x is 2? 4. 3.
No. 16.
I won't tell my Algebra 1 students. You said 6.
Is that 16?
2 to the third is 2 times 2 times 2, right? And
I
then,
did 2.
and then 4 would be 16, okay? So if I graph this, no problem. 0 goes to 1, right there, right? 1 goes to 2. 2 goes to 4. So it kind of looks like the other end of a parabola right now, but this is where it gets crazy. 3 goes to 8. And then 4 goes to 6 freaking teen, right? Okay, but now we have to go the other way because it's right now it kind of looks like a parabola. So let's go the other way. Let's say 0.5, or 0.5 is kind of weird, but we can do it. So if we say 0.5, or not 0.5, let's do some negative numbers.
-1.
Yeah, so let's do -1. What's -1? What does that give us?
So, -2. I don't know. I'm guessing.
No, because
It's
it's
just negative.
no.
I won't tell my Algebra 1 students you're struggling with negative exponents. What do you do with negative exponents?
I don't know.
We talked about
Testing
it.
It's negative.
Flip it.
Yeah,
Yes,
we want to know.
Delaney.
We just want to know if you know. Yeah.
Well, I know. I just want to see if you.
Yeah.
Why
Okay.
is it
That we were
half?
both
Why is
doing
it
the
half?
same thing.
Because you put the 2 over.
2 to the -1, you flip it. Remember negative exponents, you flip it.
no. I don't remember that.
I hate
All right.
exponents now.
I think you're.
You can say
You're-
stupid.
No, you're not
Just a
stupid.
little.
You're getting stupid. If you're not practicing.
She's like an asymptote to yes.
Approaching, but have.
God, true.
She's an something. Oh, sorry, I didn't mean. Okay, so 1/2. So what about -2? What's -2 going to give you? What's 2 to the -2? Flip it, and it becomes 1 over 2 to the +2.
-3/4.
1/4.
I'm joking. That was a
Hey,
joke.
you
got
got
the
4th
Yeah.
And then -3 is what? 1/8, right?
How do we? do
For
that?
sure.
I don't know. I had no
Okay,
idea.
we'll write it out.
Yeah, I got you.
2 to the -3. What's 2 to the -3? You flip it, and it's 2 to the +3, right? And then 2 to the +3 is 8.
Okay, I get what you're doing now. You have
Okay,
to-
so -1 goes to half, -2 goes to blah, blah, and -3 goes to 1/8. See how it's getting closer and closer and
And
closer.
eventually it's gonna touch it.
but it'll never equal 0.
I want to
Okay.
test this out.
You can just take a number on the calculator and then just divide by 1/2.
Yeah, divide by 2 equals.
Watch me do that.
It'll just get smaller and smaller.
Zero, and I'm like, well,
There
the
is a lot
calculator
of
will eventually not be followed.
Okay?
Hypothetically.
So here's the deal. You could say that the range, that the domain is your x values, right? Your domain is your x values. So this is all real numbers. All real numbers. Your range. What is your range?
0.
Well, yeah. So, but not quite 0, right? Because 0, it never touches 0. So y equals 0. That's the fence. That it never touches or crosses.
Wait, no, are negative
Aren't
numbers
fractions
real numbers?
irrational?
Negative numbers are real numbers.
So
So the domain is your
Yeah.
x values.
The
Your
domain
x
is-
values can keep going. There's no limit to your
right.
negative or positive x values. Yes.
Aren't fractions irrational?
No, those are rational, but irrational are like pi and square root of numbers you can't take the square root of. So range
All real numbers.
y is greater than 0,
Nice.
right? Not greater than or equal to, because it'll never equal 0, but y is greater than 0. Okay?
Wait, I have a question.
Yes.
So this is gonna sound super dumb. I just know it. Stupid dumb. But if the bottom line can never cross the x-axis, wouldn't there be a value over there that could never cross a line? Like,
Over here?
yeah.
No, because you can keep selecting, because your x's, your domain is what you put into the function. You can select infinite, you can select 1,000,000. It's going to be freaking high, right? But you can select any x value you want. There's no limit to your x values. But yeah, it does seem like this is going to approach parallelity too,
Well,
right?
so the line's not. So if that line can never cross that line, but that line can cross lines, how does that work?
There's no
This-
vertical.
There's no vertical asymptote, right? So there's this, but if you can imagine, see how it's almost straight right now. It's almost vertical. So you can imagine how freaking high, like 1,000,000 x value is going to be. The y is going to be. I can't even imagine how tall the y is going to be, right? Okay. So let's see here. Let's do another function.
I'm not sure I'm a fan of these.
So let's graph this. So this is an example where the b value, we're going to show you, demonstrate two different things. So y equals 3/2 to the x. And then I'm going to graph this as well. Y equals 2/3 to the x. Okay?
How do you know if something's an asymptote?
Well, exponential function like that, you'll always have an asymptote. Okay, so what we're going to do is we're going to just create some x, y values here. So x, y here would be, let's see, 0 goes to 1 again. 1 goes to 3/2. 2 goes to 9/4. 3 goes to 27/8. Okay, and over here I'm going to graph these. X and y, 0 goes to 1, 1 goes to 2/3, 2 goes to 4/9. You see how I'm getting these?
Yeah.
3 goes to 8/27. And then I need to pick some ones that are, pick some negative numbers too. So -1 gives me 2/3 because you're just flipping it, right? Flip 3/2, anything to the -1 power, you flip it. So if I flip 3/2, it's 2/3. Okay, negative 2 is 9/4. No, 8. It's 4/9, and so on. Okay, and here negative 1 is going to give me 3/2. Negative 2 is going to give me 9/4, and so on. So when I graph these two functions, here's what they look like. So we're not going to go exactly here, but 0, 1 is still right there. 0, 1 for green and for blue. Okay, 1 is going to give me 3/2, so 1.5. 1 over here is going to give me 2/3. So a little bit below there. 2 over here is going to give me 9/4, so that's 2 1/4. So it's about right there. And then 2 over here is going to give me 4/9, so a little bit less than half. Okay, and then let's go to the negative side. Negative 1 on the blue is going to give me 2/3. Right there. Negative 2 is going to give me 4/9. See how it's like a reflection of the green right there. And then green over here, the negative side is going to give me 3/2 and 9/4. So this is what this equation looks like. This is what this equation looks like. So they're inverse functions. Okay, so there are some little shortcuts here. Of transformations. So transformations are like shifting up or down or compressing. We did that when we talked about parabolas and stuff like that. But these are just transformations of the parent function y equals b to the x. Okay, so and y equals a b to the x. Vertical stretch. So vertical stretch means that it gets skinnier and taller. Okay, vertical stretch happens when the absolute value of a is greater than 1. Which kind of makes sense because whatever this number is, you're multiplying it by a number in front of that. Okay, so it's gonna get taller. All right. All right, and then you've got if it's less than 1, if it's a fraction, then it's vertical compression. Makes it shorter and fatter. Vertical compression, if a is in between 0 and 1. Okay? All right, and then you've got the normal stuff you might have seen, y equals, and other things like this. If you're adding something to the exponent, so remember when you add or subtract something to the x inside the function, then that's a horizontal shift. But then if you add something outside of the x, just add a constant, that's a vertical shift. So this is a vertical shift, which makes sense. You do all this stuff, and then you just add more to the y. So you're just adding, going up. Vertical shift, k units. And this is a horizontal shift of negative h units. Actually, my glass, I should have been wearing my glasses. They have minus h here, but I'm going to keep it like this. Horizontal shift of the opposite of that sign. Remember, horizontal shifts are the opposite of what they look like. Horizontal shift of negative h units. Or if I wrote it x minus h, it would be h units. Okay. There's some examples of graphing the functions and doing these vertical shifts and just kind of sketching them out. And they kind of prove to you that so you can see a visual of these things happening, but you don't have to do that. I would encourage you to graph some of these. Like if you're doing your homework, go to what is that? Geography or GeoGebra. That link that I always give you for the graphing calculator. Graph some of these, and so you can see what's happening visually. Yep. Okay, so we're gonna move on. Believe it or not, there's lots of application to this in your real life. Because when it comes to economics, there are sadly too many exponential equations. Like our national debt is a good example of things declining exponentially or increasing exponentially. Okay, when you buy a house, you have compound interest. When you have a credit card bill, you get compound interest. That's an exponential function. You don't want to have anything on your credit card. You don't want to have any debt on your credit card. You kind of have to have debt in certain places, like buying a house or whatever, but try to always avoid having any kind of debt on a credit card because you are paying way too much money for something you didn't have enough money to pay for in the first place, right? Some people are paying $100 for a cup of coffee because they charge it, and over time they don't pay their credit card bill. So you're paying that much money in interest. So because they're charging too much. All right. Let's move on to 48.
Right.
I like coffee.
Yeah, $100.
You can have gold in there, like gold leaf.
Oh my gosh, 5. You're gonna have 5 gold places.
Or the coffee, the coffee beans go through a cat and they poop it out. And that's like a delicacy.
The cream has to be from a cow that has 4 stomachs instead of 3.
Whoa.
What?
It must be a gold cow.
Yeah. Unless it's a chocolate milk cow. Then you can just.
That turns into a mocha.
Okay. So this is lesson 48. What'd you say? Goes through a cow, turns into mocha.
Well, we were saying
'Cause it's
the camera
chocolate?
has to be from a cow with 4 stomachs
Oh,
and is
okay.
gold, unless it's a chocolate cow, because brown cows make chocolate milk. But then that turns into a mocha, so it has to be from gold.
Yeah.
Wait, what about round chickens then? They like
They
Chocolate
eggs.
Yeah, the Easter bunnies, the little sister dudes.
like eggs made out of chocolate or like chocolate flavored eggs?
No, Jack, eggs made out of chocolate.
No, chocolate flavored.
Chocolate
eggs.
flavored eggs.
You know-
Oh.
You know, like you have a buffalo burger.
It's definitely eggs.
This is a legitimate misunderstanding I had up until recently. That not that recently, but you go and you have a buffalo burger, buffalo meat, right?
Yeah.
And then you go have Buffalo Wild Wings. I'm like, I think it's not that I really thought that, but yeah, they come from buffaloes.
You thought buffaloes had wings?
Because buffalo burgers come from buffaloes. Yeah. But anyway,
How long ago is this?
It tastes like buffalo.
I don't want to say. All right, we ready?
It's within the last year.
We ready?
No, I need to know this answer.
Avoiding the question. Eh?
Ready? Okay, so complex fractions. I always get a kick out of the way they call these complex fractions, because they're not complex. Complex fractions are just fractions inside of fractions.
But
Well, a fraction is just a division problem. And how do you divide fractions?
multiple divides. You just divide.
How do you divide fractions?
Inverse of the flip
Yeah.
on the right. Oh, wait, no.
Copy dot flop,
Yeah.
or I used to say the Napoleon Dynamite, you flip and multiply, jeez. So you have to flip the next fraction and then you, whatever. Okay, so complex fraction is just a fraction within a fraction. Okay? It's like inception. Fraction,
Did you say it's like inception?
yeah. So a dream within a dream. Fraction within a fraction. Or fractions. Fraction within a fraction within a fraction, but you have to get some kind of sedative to be able to do those problems because you can't really go that deep. Okay, so fraction within a fraction. So for example, well, let's just skip. Let's just skip to example 1. They go through method 1 and method 2. I'm just going to give you one method because it's the easiest one. Here's example 1. Well, okay. Let's just do this. Let's just simplify an easier one first. So when we had A over B over C over D, remember doing this? How do you simplify that? Well, that's a division problem, right? This fraction divided by this fraction. So that's just A over B divided by C over D. So copy dot flop. All I did was copy dot flop. So the answer to this is AD over BC, right? So copy dot, because that's a division sign, copy dot flop. Copy dot flop C over D is a D over C. Okay, that's what we did in Algebra 1. Now, and then we kind of moved.
We'd like multiply them.
Yep, yeah, if you had numbers. So we're going to skip.
3, it'd be
This is not example 1, that's example 0.
whatever that multiplies to. So
So now we're going to step it up. So in order to do this, you have to have one fraction divided by one fraction. So if you don't have one fraction, you have to make one fraction. So for example, here's example 1. 1/6 plus 3/4. Is that one fraction? Is that one fraction? No, but you can make it one fraction. You just have to add them together, right? How do you add fractions? Common denominator. So that's a 12 and a 2, right? And that's a 12 and a 9. So that becomes 11/12. And then what's that?
10 over 2.
Yeah, you could do 10 over 2 and 4 over 2. Well, not 10 over 2. No, you go.
10,
What'd you do?
10 over 5 and 1.
If you do 5
Yeah,
times 2.
10 over 5 and 1 over 5. Yeah, but
Yeah.
here's an easier way. This is just a mixed number,
It's just
2
1/5.
and 1/5. So 5 times 2 plus 1, 11/5. See what we did there? Now you could do it that way, and that's how I used to teach it. But you're going to save more time if you just recognize this is just 2 and 1/5. That's a mixed number. 5 times 2 plus 1 over 5. So copy dot flop. 11/2 times 5/11. Nice. Answer 5/2. So far, so good? All right, let's algebraic it.
That's a new word.
I want to write that down. It's going to go viral. So here's example 2A. That means there's a 2B coming. 3 plus 2 over A. 5 minus 1 over B. Okay? So we can do what we just did on the top. What's 3 and 2 over A? You could change that to a mixed number. How do you do that?
6A?
So remember, it's this number times the whole number plus the top number. So 3A plus 2 over A. You could do it that way. Is that too confusing? Because we can do it a different way. Okay, so that's 3A plus 2 all over A. We just did the same thing we did here. 5 times 2 plus 1. A times 3 plus 2. 3A plus 2. And those you can't combine because they're not like terms. All over A. All over. Now this one's a little weird. Because it's not really, it's not really a mixed number, right? Well, kind of is. You could still do that. You can still go 5 times B plus negative 1. What's 5 times b plus negative 1? 5b minus 1. So that's still a mixed number. This is just 5 plus negative 1 over b. Right? That's still a mixed number. So then we've got, now we've got a division problem. We've got one fraction divided by one fraction. That's our main goal. Because the rest, we just copy dot flop and we're done. So copy dot flop, 3a plus 2 over a dot b over 5b minus 1. Nothing cross cancels, right? And this, just forget it because they're two terms and you can't, like, even if this was an a, you can't cancel those anyway. So then just squish it all together. So you get 3a plus 2 times b all over a times 5b minus 1.
That looks awful.
Yeah.
I hate that.
So you could leave it like that, or you could simplify, like usually I'll say simplify the top just in case you find some like terms in there somewhere. But you can leave it like this. It depends on what your solutions manual say. You could say this is 3ab plus 2b, right? Just distributing that b. But you can leave it like that. Now, the alternate way, if you don't want to do the mixed number thing, the little circle thing, you can do this. We just have to find common denominators. What's the common denominator of 1 and a? Just a, right? 1 times a is a. So this needs to be an a. Whatever you do to the bottom, do to the top. This needs to be a b. Whatever you do to the bottom, do to the top. See how you get. And then when you add these fractions, 3a plus 2 over a. When you add these fractions, 5b minus 1 over b. Okay?
That sounds easier.
Yeah, and this is what we're going to have to do on the next problem. Okay? Because you can't do the fun little improper fractions on the next problem because it's a fraction plus a fraction, not a whole number plus a fraction. All right, next, 2b. So here is example 2b. Three over x plus 1 over x minus 5, all divided by 4x over x minus 5. Okay, so we don't have to worry about the bottom right now, because remember our goal is to get one fraction divided by one fraction. So the bottom is already one fraction. We're good. So how do I make this one fraction?
Whatever you did in example
2a, the alternative
The
method.
green, yeah.
So you have to find what?
Okay, find a common denominator.
Okay, what's our common denominator?
Well, I don't know for the bottom. For the top, it'd be like.
Well, you don't have to do the top.
No.
Oh yeah, we're done with the bottom.
Yeah, I was talking about like the bottom of the top fraction.
Okay.
Common denominator would be x minus 5.
Okay, now that's at first glance and what an Algebra 1 student would say, and an Algebra 2 student right after Christmas break, who's a little rusty, and that's okay. But see how these x and x minus 5 have nothing in common. There's an x in there, but there's no factors in common, right? Because factors are multiplied. This is not being multiplied. So unfortunately, the common denominator is multiplying them both together. So this needs an x minus 5. Whatever you do to the bottom, do to the top. And this guy needs an x. Right?
Oh, that looks
You guys remember doing that? It does look gross, but we'll work it out. So now we can probably do this in our head here.
It'd be 3x and negative 15x. No,
So
it'd be
3x
3x and negative 15.
Minus 15 plus 1x all over x times x minus 5.
Wouldn't that be x squared minus 5?
Don't do that yet because you're not going to want to, because when you multiply, you're going to be able to cancel those x minus 5s. Okay, but look, we've got some like terms. So we can combine those together and we get 4x. Do you see how we got 4x?
Mm-hmm.
So 4x
That's 15.
minus 15 all over x times x minus 5 dot, we're going to flop this, x minus 5 all over 4x. Now, what can you cancel? Be careful.
X minus 5.
Just the x minus 5s. Why can't you cancel that 4x?
It's fine.
Because this 4x is not being multiplied by something. The 4 and the x are multiplying by each other, but if this is 4x times a parenthesis, then you can cancel those, but you can't cancel something that's being subtracted and then divided. You can only cancel something that's being multiplied and then divided. So that's the only thing you can cancel is those x minus 5s. So you end up with, this is just a 1. So 4x minus 15 all over 4x squared. And it's heartbreaking, right? You see those 4x's over each other and you want so badly to cancel something. Just let me cancel something. But you can't. That's it.
What about the 15? Like you said, 15.
Yeah, like if there was some way, if this was like a 16, then you could factor out a 4 and at least cancel the 4s. But it's not. It's a freaking 15.
Can we pretend it's a 16?
Maybe on the next one.
Yes.
Okay.
Pretend the number is another. Okay, good. I'm just gonna do that. I'm gonna be like, well, I pretended that was the right answer on my head. I didn't write the right answer. I was pretending. You have no. Yeah, you need to pretend that that's the right answer.
Okay, this is example 3, and this is actually our life application problem. But here's what it says. A solar...
Next life. You don't need death. Okay, next life.
It says a solar collector in the shape of a frustum. Did you guys know this is a frustum?
A little trapezoid.
Or maybe it's a
It
frustum.
looks like
I don't know.
trash can.
It looks like a trash can. So it's a solar collector. So of a frustrum of a cone. So frustrum of a cone. So see how it's part of the cone, but it's the fat part of a cone, not the pointy part. All right. So collected water by freezing the sun's rays, or I don't know why I said freezing, by reflecting the sun's rays from its lateral surface toward its vertical axis. Express the volume formula in simplified form in terms of H and R. And I'm reading this, I'm like, okay, just give me a freaking complex fraction so I can get out of this. I don't care how to apply it, just give it to me. Okay, so here's the formula. The volume is pi. So this is my R. This is my H. Yeah.
Pie. It's not the actual food.
And this is my little r. So there's a big R and a little r. Okay? A big R and a little r. The big R is the bigger radius and the small r. Okay. So here's the volume of this fulcrum. Not fulcrum. The frustum.
Well, that's just
Pi r squared. No, pi h times r squared plus r times big R plus r squared all over 3. Okay.
Oh my god.
So usually a cone would be pi r squared h divided by 3. Okay. But a frustum, this r is a little different. Okay.
Because there's like an R and then there's a different R.
Yeah.
Wait, so like, what do we use this if we're like trying to like find like the dimensions of like a cup?
You could find the like that's a cup right
Yeah.
there. So you can use that formula to find the volume of a
I'm gonna
cup.
go home and be like, can I have
Okay.
a frustum of water?
So express the volume formula in simplest forms and in terms of H and R if the radius R of the smaller base is half the size of the bigger r, okay? So basically what we're gonna do is this is just half of the big R, so we're gonna substitute big R over 2 in for little r. So volume equals pi h r over 2 squared plus r over 2 squared times r plus r squared, big R squared, all divided by 3, okay? So simplify that, and we get, let's see, that's pi h big R squared. We won't distribute it, so we're just going to do yeah, this is why I don't do these a lot, but that's okay. R squared over 4 plus R squared times another R, so it'd be R cubed over 4 plus big R squared all over 3. I'm going to erase this, continue up here. So what I'm going to do now is I'm going to multiply the top and bottom by 4 times 4 times 4. Okay? Because then that will cancel these fractions. So we're kind of F-bombing it. So that cancels with that. And so I'm left with volume equals pi h times r squared plus r cubed plus 4r squared all over 12. Okay, these are like terms. Oh wait, where did that come from? Sorry. This is not a squared. So these are all like terms. So then I get pi h times 7 r squared all over 12. So that's the simplified version of it.
Yeah, so I don't know how to do that.
Yeah, you don't have to.
Oh,
You won't
that's
have anything like this on a test. It was just an example of we're simplifying a complex formula into, this is much easier than this. Okay, that's it.
Black math, give me some math and I'll give you some flack. Black math.